Okay. And Chad, you'll give me a little bit of a heads up then.
I'll stand up. Yeah, sorry, you were here. I'll stand up when you have 5 minutes.
Sounds good. Okay. Well, I do appreciate the opportunity to be here. Any chance I have to talk about forage testing and lab analysis and the application of that information, it gets me excited. And I guess it's a good thing because it's what I do for a living. It's what I do all the time. I think you'll see as we go through that this is not simply about analysis and data. It's about a whole lot more, and a whole lot more opportunity comes along with this package. So again, thank you for bearing with me. Testing procedures, past, present, future. I sort of retooled that a little bit to say, what do we consider in terms of intersecting the future through feed analysis technologies? I like to start out by making the point, and I'm a data person, a data junkie, and I will admit to that. And as I mentioned earlier, I had a professor in college at Virginia Tech, a forage agronomist, no less. And it was a class that I absolutely despised, and he taught in terms of graphs. And I hated it, but now I describe life and testing and agronomics in terms of graphs. So I don't know if there's a connection there or not. But if we look at a distribution, and in a distribution, if it is something that we can measure, and if there is range, I look at it as opportunity. It says that if anybody is functioning or engaging a production function, whether it's agronomic, whether it's financial, whether it's personal, if there is range, it says there's opportunity to get up in the morning and to be excited and to move from somewhere down at this end of the range up to this end. So if somebody is a producer, if they are engaged in agriculture, if they are challenged at times by circumstances or economics, there's always opportunity, and it's how you look at it, perceive it, engage it. But when I see a distribution graph, I get excited. So feeds testing, it's not just for ration development. It's not just numbers that are on a paper that go in a corner. Feed testing methodologies are tools to generate decision information. They're tools that create platforms from which we can advocate change. And that then provides us an opportunity to be excited as we get in front of those that we serve, that we invest in, that are our clients or otherwise. So, not all concepts that I'm going to talk about are necessarily applicable for where you're at, but I would say that the objective is to think out of the box. We can always work to think out of the box. And I would say, how can we use forage and feed evaluation procedures to produce change? That's what we're about. Most all of us in this room at one level are about producing change. So the issue is, the focus is sorghum, Sudan, and how we look at that from an analytical standpoint. I would put up here a crude protein distribution. And this is going back into our database, about 6,000 samples with an average of 11.5 approximately. And what do we see? A very significant range here. And that points out that there are opportunities, and there are also probably some challenges as we look at that. Keep that in your mind. If we look at this database again, about 4,000 samples in this case, and we look at starch, we see a very significant distribution where we have a lot of samples in the 2 to 4% range, but we have samples all over the board here. 2%, 10%, greater than 20%. What are we defining?
Ralph, does that include dry hay and silage?
These are silages.
Just silage.
Just silages, that's correct. And feel free, anybody has questions or comments, jump in. So again, we look at that one. We look at sugar distribution, and I see a lot of opportunity in this graph. And I see that because most of the time in fermented feed materials, I expect the fermentation to utilize the sugars and drive them down very close to 1 to 2%. But with sorghum Sudans, I've got a tremendous percentage of samples that are carrying higher levels of sugar. And I say, that's different than traditional forages that I see and analyze. So there's opportunity. But again, look at the range. Oop, I backed up, but that's not all bad. With the ranges that we're looking at here, part of the problem is that we do not, in the industry, in the testing industry, in the field, we do not properly characterize the materials that we are working with. And because of that, the information that we develop and apply has much less value because we don't know what are the characteristics of a given type or maturity of feed material and how does a given sample compare to the norm for that cluster of samples. And so I would say that the opportunity for the industry, and particularly for those that work with sorghum, that sell sorghum seed, that look at sorghum as an opportunity, I think we need to invest in better identification and labeling. That's absolutely critical so that as we generate data, as we pull this data, as we work with it, it means something to us. So, classification. We need to agree as an industry on appropriate definitions. We need to communicate those to the industry in some fashion, and we need to push for use of these terms when labeling samples for evaluation or in general describing them as we're working with these materials in the industry. Okay, management of forage testing data. It's a big deal. And when I talk about that, I talk in terms of Forage Lab Information Technology. A definition I would give to that is the collection, management, analysis, and reporting of information to allow for increased understanding of the production and management of ruminant feeds, systems of feed delivery, and the modeling of rations leading to improved management and decision processes. So we're engaged in a process here. We're going somewhere with this. So, in this process of data management, of IT, integrity of information, you would all agree, is a pretty critical issue. And because of that, we have taken the step of developing a field app that, I don't have my tablet with me, you can download from the App Store, that allows those in the field to become the responsible parties for administration of information. It provides the opportunities for the integration of a lot of additional meta information, the opportunity to define and force responses that is not always available through traditional means when we obtain forages from the field. And there's an opportunity to incorporate a lot more information than what we can write on a bag or put on a piece of paper. Now, this is not an atypical approach to how we receive samples. Now, in the laboratory, we can get 600 to 800 samples or bags or submission in a day's time. Now, to the degree that they're labeled like this, it creates overhead because not everybody is able to decipher that. And we have, when we're busy, several gals, they can spend 2 to 3 hours apiece making phone calls and working to decipher what the intent was in that type of labeling. That's a problem. You can relate.
That much information at times.
I'm sorry?
You actually get that much information.
Oh, and yes, I agree. We've got in our refrigerator, our dead box, samples that don't even have labels on them. So, with that in mind, how can we solve that challenge? Well, through our field app, we have the opportunity to script out the information that we're looking for, to give the user a chance to take a source photo, to set GPS coordinates, to be able to add additional information. For instance, we could have a drop down where when we are defining sorghum, Sudan, all of a sudden it's not a field where they write in a description. It is a set of checkboxes that challenge them to properly define what they're sending in. Better information. Okay, and then they can also add notes concerning the use of the material that they can access later. They can define user labels, so if you're out, you're doing research or particular company trial work, you have the ability to, in effect, use this backbone for data collection. So, if we're looking at the hay market, if we're looking at creating basically an audit trail to validate, working with a large hay company that exports to Asia. He sat at his desk in California and he pulled out a report that came from the Chinese government. And that report said that the alfalfa that he had shipped over was 6% protein. And they had a problem with it at 6% protein. They were creating leverage. But if we have, through an audit process, through a certified process, the ability to produce information and an audit trail, now we can push back. Now we can create credibility in the marketing chain. And so that is part of what this app will allow us to do. So information integrity, we open the app, we scan the barcode, the field person logs the sample. There's minimal information that goes on the bag now, no paperwork. You send it in. The information precedes the sample to the lab. So the app's established in the database. It can be amended by the user through the web. There's a record of that submission that's emailed to the user. The lab receives samples, scans it coming in, and we are off and running. This is what in the App Store it looks like. This is a field in terms of information collected. We can even check categories for sample volume. So it implies that we want certain sample volumes coming in from the field. They can attach source photos that they can access later. We take lab photos of everything in the lab that the user can access. It's part of the record. This is what they see if they want to access results through the app. Some of the other things that we're building into this include growing degree days based on GPS location, rainfall, heat index based on location. So we're attempting to round this out and make it a full utility. Then when they get a forage report back, they get the typical information that they would want to see, but then we have the opportunity through technology now for them to be able to use a QR scanner, scan that, and that gives them a listing of all the terms and the background information associated with that sample analysis. Or if we're talking about sorghums, we're in the process of developing a set of distribution graphs, averages, and information to back that up that they can access through that QR code. Now, let's say there's additional metadata submitted with that sample, source photos, notes. If they scan this QR code, it takes them right to the database where they can see that information. So again, platform for data management. So we have opportunities in terms of establishing definitions, creating protocols, creating systems then for summarizing and reporting of data. Going to shift gears here a minute. Here is a problem and an opportunity in the realm of sorghum Sudan forage. And you notice that I didn't put a label on that distribution graph. But I would ask you, in looking at that, does anybody have an idea when it comes to that forage class, what particular nutrient or characteristic would be problematic that would be defined by that distribution? And okay, nitrates, no. And it's in particular an issue more so with this feed class than any other feed class. Ash. A nominal ash level for aggregate sorghum Sudan, and we're talking a broad category, it's right around 9%. Look at the percentage of samples with significant ash levels above that. That represents contamination. And that creates very significant problems at multiple levels, in the laboratory, in the field, in terms of the fermentation, in terms of the material put in front of the animal. It's an opportunity. It's a management opportunity.
What's causing that decreased ash level?
I think that part of that comes with the magnitude of the size of the equipment that we're now using. I think it also comes with the significant adoption of disc binds for cutting material. I think, again, we do that. We cover larger acreages. We're moving faster. I think a lot of times we just absolutely tear off the gopher hills and keep moving, and maybe more than that.
Well, I think the sorghum beans can be sticky at times. They're almost like it's thicker than corn wheat and all the dust is simply the volume of meat. And it seems like the dust is clinging to those meat. I don't know why, but it does seem that simply they pick up the dust and hold on to it.
I appreciate that from a field perspective. Very good.
The other one could be used when you're mowing it down and so forth, the ground contact and the use of wheel driven rakes rather than power rakes,
Okay.
especially on wet product. The other thing that could add to it a little bit is if you're doing it with external moisture on the plant when it hits the ground. Any dew or anything, you're getting out there, you got to get out there to get it done, but you're getting out there too soon with the dew on it. Contacting with the ground, you're going to pick up more dirt with any kind of rake.
I agree. And again,
I think a lot of it more is raking because with the sorghum and Sudan crops, you don't have a number of stubble plants there like in an alfalfa field or a grass field, and the stuff falls on the ground. It's not up on the stubble like a lot of the grass crops do.
All those things are contributing factors.
okay. Great. And again, there's opportunity then to educate and to attempt to move beyond that. Now, one of the challenges in the laboratory with this is that as we do fiber analysis, traditionally in a laboratory setting, we do fiber extractions, fiber recoveries, but the challenge, the problem is that the fiber recovery is based on solubilization of materials. What is not soluble in neutral detergent solution, we refer to as NDF. What is not soluble in an acid detergent solution, we call ADF. It may be organic matter based, or it could be ash contamination. And that significantly confounds our perception of quality and our understanding of the characteristics of feed materials, sorghum, Sudan, at the top of the list. So if I look at 200 samples that I pulled and evaluated, I ran them in the laboratory in a traditional manner. Then I took the residue that I recovered on my filter paper that I called NDF and I ashed that material. And then that allowed me to subtract out or remove the ash component. This would be the distribution of differences between NDF done in a traditional fashion and NDF done on an organic, what we would call an organic matter basis. Now, a lot of samples, it's 1 or 2%. The mischaracterization is not that big a deal. But if you are a forage producer or a forage user, if you're working with high-producing dairy cows, and you're mischaracterizing your forage by 5, 6, 7 points of NDF, do you think that's a big deal? That is huge. And that's a problem. It's a problem for the person using it. It's a problem for the forage producer, because now the perception is that the material is of lower quality, more mature than it really is. So we need to be moving towards doing fibers on an organic matter basis or ash-free. So the lab needs to recognize this as an analytical problem. They need to provide evaluation of fibers on an ash-free or organic matter basis. And not only NDF, but NDF digestibility is hugely impacted by this same confounding mechanism. Here is a sample of forage material that I took from one of the pictures that's associated with a forage analysis in our system. And this one has probably 10 plus points of ash contamination, not that you could see it. And if we go through and do the NDF based on a traditional method, we come up with a 54.6. And if we do a NDF digestibility at 30 hours, we come up with a 56. Well, that's so-so material. You know, it's not great, not awful. But if we go and do this on an ash-free basis, that NDF now becomes a 48%. We went from an average material to something that actually is pretty darn good if it weren't for the ash contamination. We went and picked up a whole 10 points. And don't challenge me on the math, because I know I'm right. Okay. Yeah, scares me. So anyway, there's a tremendous difference in our characterization of that feed material because of the ash contamination. Let's take another sample. This looks like something that's relatively fresh but still has 10, 11% ash contamination. Again, you wouldn't tell it. We can get materials with 20, 25% ash contamination, and unless you really look at it, you can't tell that it's there. So let's look at this material. We have an NDF of 60. From a dairy standpoint, that's starting to get a little marginal. We have a digestibility of 50%. Again, a little marginal. But look what happens when we do it on an ash-free basis. The difference is huge.
Now, that's my point. That's what I was thinking about, all right? That ash is still being consumed by the cow. How is it affecting the rumen is the ultimate thing.
And that is, to me, that is a key point. And I have pushed various academics and nutritionists on this, and I would like to see some specific evaluations or studies to this end. And my contention is that dry matter intake, which is what we're primarily concerned with here, we want to maximize organic matter intake and digestibility in the cow. So to the degree that this ash impacts dry matter intake, I have been disadvantaged. The question is, or the way I look at it, dry matter intake is significantly dependent on gut fill, which is related to NDF or indigestible NDF. I don't perceive that it's significantly related to ash, inert ash, because there is not a volume effect. There may be at some level some distension effect, but it is not truly a gut fill effect like NDF. My contention would be picking a dairy ration, because that's what I'm familiar with. If you have a group of cows averaging 54 pounds of dry matter and you drop 2 pounds of inert material, ash, into that, my expectation is they're going to come pretty close to eating 56 pounds of dry matter. And if that's the case, all things being equal, that ash has not impacted other quality factors in that forage, and that's a big question mark, then the fact from an organic matter basis, we may actually still have a good material. Now, again, that ultimately we want to characterize it in a way that reflects animal response.
I'm not so worried about the intake. I'm worried about the actual effect in the rumen on the bugs. Okay?
And I agree, I'm not going to go there at the moment.
Yeah.
And I said all other things,
Yeah.
so point well taken. So we come back to an issue of needing to engage proper management, harvest in a manner to minimize this as an issue, engage that crop in a way to maximize a productive fermentation. So management opportunities here. Now we're getting around to an area that I think is of particular importance to folks, and that is how do we assign estimates of energy to feed materials like these sorghum Sudans. If I look at our database, I have a distribution of TDN, and if I look at it from an NEL standpoint, again being dairy focused, I see this. Now, got a little bit of a double hump there. Why is that? Well, why do I have a group of forages that seem to average maybe 0.58, 0.6 NEL, and then it looks like I've got a group that averaging 0.68? That's a possibility. I think there's another one in there. I didn't hear that. Yeah. What are we dealing with sorghum Sudans? Traditional and BMR. And as I look at that, particularly being engaged with it on the corn side, I think part of it is the degree to which we have grain, but I think more significantly it's the degree to which we're engaging vegetative BMR species. The difference is huge, and we need to recognize from an energy standpoint there are differences. So, there's some concerns that the forage analysis systems do not account correctly for energy or the opportunities with BMR. Some would advocate adding a factor, 0.1, 0.2, whatever, to the NEL. My contention is that the systems for generating estimates of energy that we use in the laboratory are mechanistically based, and it should apply to sorghums really no differently than it applies to any other feeds, as long as we are moving beyond a ADF or NDF-based system. So, calculating appropriate energy values is dependent on getting good data for, in particular, NDF, ash, and then either lignin or NDF digestibility. Both speak to digestibility. And then the appropriate incorporation those into a summative equation or mechanistic equation. So, some labs do not have true sorghum Sudan NR equations for predictions. That can be an issue. If there is ash contamination, that has to be accounted for to get correct energy values. And not all labs have NIR equations that do a good job of predicting digestibility type information. Lignin and NDF digestibility are two of the newer and more difficult assays to execute. And sorghum isn't something that's at the top of the list. There has not been the attention or the investment in NIR to do a good job there. Let's look at the impact of modifying some nutrients and how it impacts our perception of NEL. And I'm choosing a little bit of an exceptional case as opposed to an average sample to make the point. Let's take that baseline sorghum Sudan, where we have an NDF of 48 with no ash contamination. We have a relatively low lignin. And I think we always need to look at lignin in reference or relationship to NDF. It's that lignin-NDF ratio that describes the product or its digestibility, not just the lignin per se. So we look at that and we generate a 0.746 NEL. Now, let's take that same material, but say that it's a BMR, and that instead of traditional digestibility, we now have a lignin that's much lower, and we can capture that lignin properly. Look what simply shifting that lignin does, the perception of fiber digestibility does to the NEL. It kicks it up tremendously. Now, let's take that same sample, and let's throw in about 10% ash contamination. From there, we do lignins on an ash-free basis, so it doesn't impact the lignin. But we don't necessarily do the NDF that way, so now we have ash contamination, and we perceive a 53% NDF and a different lignin-NDF ratio. Look what happens to our NEL. The ash contamination just undermined the perception of quality or validity of that crop. That's a big deal. So let's then throw the ash in, but we do the NDF on an organic matter basis to bring it back to where it should be. Now we're at a 0.62. still have a problem. Why? Well, ash takes up space. It dilutes energy. So if we've got ash in there, we don't have as good a product. Let's say the lab does a bad job with the lignin. And let's say that instead of it being 4.19, the lab comes back and says it's a 5.6. Well, instead of a 0.75, we got a 0.72. So the job that the lab is doing can impact that. And then let's say the stuff gets mature on us. We don't have ash contamination, but it gets mature, and our lignin goes up as a result. Instead of having the 0.75, we're down to a 0.7. So these would be some of the means, the ways in which characteristics would impact that NEL value. Now we can do the same thing and substitute 30-hour NDF digestibility, which is a little bit better evaluation of digestibility than simply lignin, and we basically see the same impacts as we go through that. It's just a different way of getting at digestibility. So, as we evaluate energy, perceptions may lead to the expectation that forage materials are feeding better than a lab analysis, but there are reasons for that. So don't throw out, as they say, the baby with the bathwater. Take a step back. Why are we not able to reconcile what the animals are telling us with our perception of forage quality? Samples with ash contamination are an issue. BMR may feed better because of a greater rate of passage, though, not related to what we get off the forage test. And we certainly see this with BMR in corn silage and dairy cattle. Now, to me, big issue here. Always remember that energy values are assigned. They are a static estimate of how a material will perform. True energy values actually are the result of feeding a material into a given ration in a given animal system. So often we want NELs or TDNs and we think that they're the end-all. Technically, they're the result of. So let's not get always so hung up on that NEL. Okay, shifting gears a little bit. Different approaches to evaluation. I took a material through and I did it by chemistry. I did it by an NIR sorghum equation. And I did it by a corn silage equation. Labs that don't have a sorghum equation, guess what they do? They'll put it through a corn silage equation. It may or may not work. Now, we have very large, very robust equations. I was looking for a train wreck when I did this, and I didn't find a train wreck. I guess that's good. We see that we're off a little bit on our corn silage protein, but our other numbers lined up pretty well. But just be aware that this can be an issue as we're sending materials to laboratories. And with that, we need to ascertain that the laboratories that we're working with have appropriate NIR equations to do the job. And we really ought to be able to get from them, what are the number of samples in the NIR equation? What's the average and standard deviation of the population that was used? Does it fit the materials that I'm wanting to test? What's the R-square of the calibration? And most importantly, what is the standard error of validation?
You don't report, when you give somebody a sample back and you run NIR, you don't report a global H.
We do not, but what we do, and on our forage reports, in a step in that direction, and eventually we're going to be doing that, but in a step in that direction, we report out a qualitative evaluation where we will say that a sample in a given calibration has excellent prediction potential, average prediction potential, or poor prediction potential in order to give the user the opportunity to get at that global H.
So how do you, like say you ran a sample through your lab, it was like a global H12 or something. What do you do with that number? Do you still report those values?
We put that back through. Generally, we will report that with a note that says values are being verified by chemistry. And if we go back to, this sample, when we have a global H here under a sorghum equation of 0.85, and with global H, it's basically a statistical measure that says that that sample, the spectra, relates very closely to the population spectra used to predict the answer or the analysis. And when we did it under corn silage, it said the spectra of that didn't look anything like a corn silage. So it doesn't mean that our analysis is wrong. It simply means that the probability of it being right is lower. It's a little different. Moving on.
What is your global H cutoff in those types of equations?
If you would, hold questions a minute till I finish out, then I don't get my neck in a noose here. Oops. So, as an example, let's look at a good calibration statistics. Number of samples for an NDF equation, 1900. Population average, an R-square of 0.97 and an SECV of 0.88. It's pretty darn good. Wish I could do that on all constituents. But we also have the other side, where somebody puts something together on a limited number of samples. And there are a lot of analysis done by labs that put equations together that simply because they have an equation and the machine generates a value, they publish it. And we can take 100 samples and we can have an R-square of 0.84 and an SECV of 5.3. That doesn't mean that the lab won't publish that. The quality of what comes out underneath of this equation is going to be quite a bit different than the quality of what comes out under that equation, right? So finishing up, UNDF, undigestible NDF, is something you will hear more about. We do that by looking at, historically, it was determined or estimated as lignin times 2.4. We do it by incubating samples in an in vitro system for 240 hours. So it's not an easy test to execute, but we do have calibrations. We actually have a system here where we can incubate 1,800 flasks at a time in a traditional in vitro system. So we do have calibrations for undigestible, indigestible NDF. This is what it would look like for sorghum. And more importantly, if we look at forage material, sorghum material, and we look at the distribution of undigested NDF as a percent of dry matter, we see very significant range. Basically, what this says is if we feed this material to cows, samples that are up here are going to very quickly impact dry matter intake. And we will not get animal productivity. If we generate materials with UNDF levels, total UNDF levels down here, we have a product that is marketable, that has value, and that will allow animals to perform and will fit in high quality animal rations, dairy rations. So it is something to track. And I'm just finishing up. If we look at BMR in corn silage, we have two populations there of UNDF. This population is conventional. This population is BMR. They're almost two totally different populations, aren't they? Well, basically they are. And I would contend that with BMR in Sorghum Sudan, you have much the same thing and you need to exploit that. In the future, some of the things that we're going to be looking at and working with as it relates to Sorghum Sudan. And we will skip the conclusion, and I thank you.
So one question, Rocky, what is your question? When you look at those global H for the different equations, what is your maximum cutoff on those?
Okay. I feel comfortable with global H's in our system up to about 2, a little over 2. Generally, there's not a whole lot. I see in our system that we'll get a certain percentage of samples up to 2, maybe 2.5, and then there's a break point, and then they get quickly quite high. So we do two things. We look at the global H, and then we also statistically look at the results to say, are they consistent with the feed class and the cluster for which we're evaluating. So if I were going to give an answer, I'd say 2 is kind of our break point.